Hello, my name is Monica and Zee,
And I'm Zee,
and we are going to present about the atomic force microscopy or AFM. Here we have a diagram we are familiar with, detection range versus analytical spot size for several characterization techniques. The atomic force microscopy is located here and is classified as an imaging technique. As you can see, it has a very good analytical spot size or resolution. As other microscopy techniques, AFM allow us to get information only of the top surface of our sample as is shown here. Differently from other microscopy techniques, AFM enable us to get an image in 3D of our sample. AFM belongs to what is called scanning probe techniques. The first of these techniques to be developed was STM or scanning tunneling microscopy. Later, AFM was developed as a modified version to be also used in non-conductive samples. Other techniques were also developed in the following years. Still, STM and FAM are the most popular. Here you have the atomic force microscope original paper, and the first author was also awarded the Nobel Prize in 1986 for his participation in the development of the scanning tunneling microscope. Now we will talk about the components of AFM. Here is a schematic diagram showing each of the components of this technique. In the previous diagram, we had a sample placed in a holder which was attached to a tube. This tube is known as piezoelectric scanning tube. Here you have a more detailed image of how it looks. Basically, it's a cylinder of a piezoelectric material connected to 5 electrodes. Piezoelectric material is that one that shows the property of piezoelectricity. In simple terms, when a piezoelectric material is deformed, a voltage develops across it. It also works the other way, so when a voltage is applied across this material, the material is deformed in that direction. The next set of components are shown here. It's the cantilever and the probe tip. Here you have a real cantilever that can come in several shapes, and it's usually made of silicon or silicon nitride. The most important characteristic is that it should have a low spring constant. On the other hand, we have a real probe tip that can also come in several shapes. This is the most important component of the AFM, since its sharpness is what determines the resolution of this method. The next components are the PSD and the diode laser. The diode laser provides the laser beam, and the diode works as a detector. The PSD is a junction diode that when light is illuminated on it, a final voltage is produced. This voltage is a function of the distance to the center or the edges. For example, in general, when the light is shining at the center, there will be 0 voltage generated. When it's in some other position, the voltage will be finite. For example, we can say it is 5 millivolts. You might wonder what happens in this case since all the points have the same distance. Well, all of them produce a voltage of 5 millivolts. However, the diode is connected to a computer interface that can give us the specific coordinates of the point in which the laser beam is shining. So, those are all the components we needed for the AFM microscope, and you can see the completed diagram here. Now it's time to talk about the AFM operation principles, which are 3: surface sensing, laser detection, and surface imaging. Surface sensing, which occurs between the tip and the sample, is governed by the interatomic interaction forces, also called van der Waals forces or induced dipole interaction. In an atom, the electrons are fastly oscillating around the nucleus, so at a given moment they are identified as a charge localization. This charge induces a charge of the opposite sign in the neighboring atoms or molecules. Then, an attraction force arises between them. The localization changes position in time, so the attraction is dispersed around the entire bulk of the material. In the case of our interest, this interaction between surfaces is proportional to the the inverse of the distance squared between the surfaces, and it scales up to 100 nanometers. The interaction between the surfaces is characterized by a general potential curve. For distances greater than 100 nanometers, there is no interaction as the van der Waals force scales up to this distance. For intermediate distances, it's the van der Waals attractive force that is dominating. For distances less than a critical distance, there is electrostatic repulsion or Coulombic repulsion. This arises as the electron clouds of two atoms get in physical contact. In the case of AFM, we have surface-to-surface interaction between the surface of the tip and the surface of the sample. The next operation principle is the laser detection, which relies on the beam bounce method. The laser is reflected in a shiny surface at the back of the cantilever towards the photodetector. An important initial step in the laser detection is the alignment. We have the detector, the laser, and the cantilever. The cantilever needs to be placed right in front of the laser beam, so it is reflected and falls into the detector. However, it is not properly aligned. The position of the detector can be modified, so the laser beam falls directly into the center. It can also occur that the cantilever is bent or can also be deflected, so the laser beam will fall somewhere else other than the center. This can be fixed by applying a voltage to this region that is called the piezo of the cantilever. When a voltage is applied, this will expand and will realign the cantilever to a proper position, and the laser beam will fall again into the center of the detector. Understanding the steps mentioned before is very important because they are very relevant for the imaging in AFM. Here you have the aligned AFM, in which the laser falls directly into the center of the detection. If the cantilever bends or is deflected, the light will fall somewhere else. This occurs as the cantilever moves across the surface of the sample, and it can be realigned into the center of the detector using the piezoelectric attached at the end of the cantilever.
There are three different modes of operations for AFM, and they are contact mode, non-contact mode, and tapping mode. Depending on the distance between the tip and the sample, or different force interaction between those two surfaces, the deflection of the cantilever changes, as seen from the diagram. As cantilever approaches the attractive force region, the tip bends towards the sample surface. But as the distance between the tip and sample gets even closer, repulsive force becomes stronger, making cantilever deflect away from the sample. Since the interatomic force is a weak force, in order to have sensitive AFM apparatus, it is important to use cantilever with low spring constant, as it would increase the deflection distance according to Hooke's law. Below are the examples of secondary AFM imaging techniques that corresponds to each mode of imaging. In contact mode, the cantilever is directly in contact with the atom of the surface, assuming our model, that is, with interatomic distance of less than 0.8 nanometer, making the main force of the tip a repulsive force. Contact mode has two types of modes, and all imaging methods involve relative changes in the user-defined point or set point on the photodetector. Constant height mode maintains piezo height, and it measures differences in deflection or bending of cantilever as tip drags through the sample. After collecting XY coordinate data and deflection, image is generated in respect to the change in deflection in grayscale. Constant force mode maintains same deflection of the cantilever. When cantilever experiences change in force through elevation, Z piezo recalibrates the deflection by moving upward or downward, and image is generated in respect to the change in Z piezo in grayscale. Advantages of contact mode is it allows fast scanning of sample, as the tip is in direct contact with the sample surface, is good for rough samples, and has high resolution in AFM imaging methods. Of these two modes, constant force mode is preferred, as cantilever is dragged through the sample and applies frictional force on the sample in constant height mode. This can damage soft samples, like organic samples, and wear out the probe faster than constant force mode. However, constant height mode does have merit that it can scan faster than constant force mode, since constant force mode speed is limited by the response time of the feedback circuit. So constant height mode is occasionally used on atomically flat surfaces. Even if the sample is topographically flat, there may be different domains of different surface properties. Even when the elevation of the sample is the same, there may be lateral deflection of the cantilever due to difference in friction, adhesion, and surface tension in different regions of samples, which may indicate different materials were used in different regions. Lateral force microscopy takes these differences in lateral deflection and maps different composites or different components or regions in the sample, as shown in the diagram. In force modulation microscopy, cantilever deflection remains constant, but driving signal is applied, making the tip or the sample vibrate. When tip comes across hard sample, the surface will resist the tip, making cantilever deflect or bend, increasing the amplitude of the oscillation, while the soft sample will dampen the oscillation, causing differences in amplitude and waves, and these differences will identify each region of the sample. Intermittent contact or tapping mode is similar to constant height mode or contact mode in a way that the scanner moves along the surface at a fixed amplitude while cantilever oscillates above the sample at resonant frequency. Cantilever's amplitude is set that scanning is done in the attractive interaction regime and occasionally taps the surface of the sample if the sample is close enough to attract the probe. After tapping the surface, feedback lifts the Z piezo to return to user-defined amplitude. When there is change in height or oscillation, the feedback loop registers the differences in the amplitude and the image is then made from the differences in the amplitude. Advantages of tapping mode is that it allows high resolution of samples that are easily damaged or loosely held to a surface. So that's why it's commonly used on biological or organic samples when they need high resolution. Phase imaging is a secondary imaging technique of tapping mode. As cantilever oscillates, it forms waves with certain frequency. But as the probe comes across the sample with different surface properties, it may experience a slight delay. For example, if the probe comes across with a region with higher adhesion or attractive force, it will hold on to the probe for a few nano to picoseconds longer than previous regions. If lateral force microscopy tells apart different regions with the deflection of the cantilever, phase imaging tells apart regions from differences in phase lags or pauses in the waves. Non-contact is similar to tapping mode, but differs in the point that it maintains constant amplitude between the probe and the sample. Non-contact mode detects changes in the Z piezo when tip comes near the sample surface, as piezo adjusts the height to maintain the same amplitude of wave. Advantages of non-contact AFM is it exerts least force on the sample, so it does not damage the sample and ensures extended probe lifetime. Disadvantages are it has the lowest resolution of the imaging methods, and probe may register water layer as a sample surface. In order to deal with this problem, ultra-high vacuum is needed for best imaging. Finally, we'll discuss the effect of tape sharpness on resolution of sample. AFM's feature resolution is not limited by diffraction of illumination source like other analysis techniques, but is limited by the dimension and geometry of the tip or probe. Larger tips have a hard time distinguishing close adjacent features or holes in the sample, as the tip cannot go inside the little gap. Sharper tips can therefore give higher resolution, but it can be challenging to make ultra-sharp tips due to technological constraints. Geometry of tip can also affect the image, as for example, spherical or blunt tip can have a hard time distinguishing edges of the sample. This is also a problem with a tip that wears out after long scanning, as tip can become blunt after it experiences too much frictional force through dragging on the surface. So these are our references, and thank you for listening.